we're going to talk about descriptive statistics and inferential statistics. We're going to talk about descriptive statistics this week and inferential statistics next week. Statistics have to do with dealing with your raw data, trying to see what patterns you have. Inferential statistics makes determinations, and so that is the difference between the two. So let's go ahead and start talking about descriptive statistics. There you go. Okay. I'll have to admit that is not my favorite topic. I've taught it a lot. Well, maybe not too much, not that much. Anyway, it was really kind of interesting because 2 or 3 summers ago, my we hired my son to teach statistics. This class, and he has a master's degree in applied mathematics. So he should be able to teach statistics, but when he looked at the statistics text, he discovered that the statistics that he talks about was completely different. And this is one of the reasons why, sure, you can take the mathematics statistics class, which I think is MTH 213, if I'm not mistaken. But you can do it if you like, but you're not going to get the same information because social science statistics look at different aspects. They put things together a little bit differently. Are they statistics? Of course, they're statistics. Mathematicians can figure these things out, but they are a little bit different because they use different formulas. They're looking at different things, and the thing that the aspect that convinced my son that he may not be able to do this was Cronbach's alpha. And we're going to talk about Cronbach's alpha in just a minute, but he had never heard of Cronbach's alpha. And he was kind of embarrassed. And then he looked and he found Cohen's d and other terms that he had never seen before. They made sense to him, but a lot of statistics have more to do with probabilities, and since psychology, since the social sciences, there are very few absolutes. In mathematics, there are absolutes, but there are hardly any absolutes in psychology or social science. The social sciences, it was they use different formulas, different type of statistical analyses. And for that reason, he decided he couldn't do it. So I taught the class instead. So today we're going to talk about descriptive statistics. Descriptive statistics refers to the set of techniques for summarizing and displaying data. As I said before, it has to do with raw data. Inferential statistics, of course, you're trying to make determinations. But descriptive statistics is just the raw data, presenting the material or presenting the results in numerical form. If the data is quantitative and consists of scores on one or more variables for each of several study participants, we need descriptive statistics to discuss it. Qualitative research, it's sometimes you can assign numbers. Quantitative quantitative statistics, quantitative analysis, of course, quantitative research. You're determining numbers, like your score on a Beck's depression inventory. Is that absolute? Well, of course it's not, because you're being subjective. But it's still numbers, and you can still do statistics looking at it, even though it's not an absolute score. We're not going to look at a select individual and say, oh, your depression level is a 7.213. And the next guy looks at him and says, yeah, he's a 7.213. I can see it from his results. That's not really going to happen. The way Beck's depression inventory works, it's very subjective. and you'll get a number like 5 or 7 or whatever. But it isn't an absolute. It's very subjective, and because psychology and social sciences are so subjective, that's one of the reasons why the statistics are very much different than you would see in applied mathematics. In most cases, the primary research question will be about one or more statistical relationships between variables, but we also need to describe each variable individually. For this reason, we will look at some of the most common techniques for describing single variables. So when we're talking about variables, in my own research, and I've used my own research quite a bit in this class, we were looking at age, gender, education, level of trauma, and cultural awareness. Those were my independent variables, and my one dependent variable, of course, was resilience that we measured from a resilience scale. Now, were those numbers absolute? Of course they weren't. You really can't measure somebody's resilience. You can't draw a tube of blood and run an analysis and find out what somebody's resilience is. Resilience has to do with your mindset. So it's not an absolute number either. Every variable has a distribution, which is the way that scores are distributed across the levels of that variable. For example, in a sample of 100 university students, the distribution of the variable number of siblings might be such that 10 of them have no siblings, 30 have one sibling, 40 have two siblings, and so on and so on. In the same sample, the distribution of the variable sex might be such that 44 have a score of male and 56 have a score of female. One way to display the distribution of a variable is in a frequency table. The table to the right is a frequency table showing a hypothetical distribution of scores on the Rosenberg self-esteem scale for a sample of 40 college students. The first column lists the values of the variable, the possible scores on the Rosenberg scale, and the second column lists the frequency of each score. This table shows that there were 3 students who had self-esteem scores of 24, 5 who had self-esteem scores of 23, and so on. From a frequency table like this, one can quickly see several important aspects of a distribution, including the range of scores from 15 to 24, the most and least common scores, 22 and 17 respectively, and any extreme scores that stand out from the rest, and that would probably be 22, since there were 10 people that had self-esteem scores of 22. The levels listed in the first column usually go from the highest at the top to the lowest at the bottom, and they usually do not extend beyond the highest and lowest scores in the data. Why in the world would you put something in there that was all zeros? When there are many different scores across a wide range of values, it is often better to create a grouped frequency scale, and this is what a grouped frequency is. 241 to 260, 221 to 240, that is grouped. The first column lists ranges of values, and the second column lists the frequency of scores in each range, and that's what we have done here. The table to the right is a grouped frequency table showing a hypothetical distribution of simple reaction times for a sample of 20 participants. In a grouped frequency table, the ranges must all be of equal width, and there are usually between 5 and 15 of them. Frequency tables can also be used for categorical variables, in which case the levels are category labels. The order of the category labels is somewhat arbitrary, but they are often listed from the most frequent at the top to the least frequent at the bottom. A histogram is a graphical display of a distribution, and this is a histogram right here. So is a scatter plot. It's a histogram. It presents the same information as a frequency table, but in a way that is even quicker and easier to grasp. The histogram to the right presents the distribution of self-esteem scores that we saw in the table, but now we have it in a graph. The x-axis of the histogram represents the variable, and the y-axis represents frequency. Above each level of the variable on the x-axis is a vertical bar that represents the number of individuals with that score. When the variable is quantitative, there is usually no gap between the bars. When the variable is categorical, there is usually a small gap between them. The gap at 17 in this histogram reflects the fact that there were no scores of 17 in this data set. And as you can see, this is an empty slot. When the distribution of a quantitative variable is displayed in a histogram, it has a shape. The shape of the distribution of self-esteem scores is typical. There is a peak somewhere near the middle of the distribution and tails that taper in either direction from the peak. The distribution of self-esteem histogram is unimodal, meaning it has one distinct peak, but distributions can also be bimodal, meaning they have two distinct peaks. The bottom histogram shows a hypothetical bimodal distribution scores on the Beck depression inventory. Distributions can also have more than two distinct peaks, but these are relatively rare in psychological research. So we have a peak at 10 to 19. We have a peak between 50 and 59. Another characteristic of the shape of a distribution is whether it is symmetrical. Most of them are shaped like a mountain, as you can see. We have two mountains here. There we go. And this one has one, goes up, and then it comes back down. It looks like a mountain. Another characteristic of the shape of a distribution is whether it is symmetrical or skewed. In a symmetrical distribution, the left and right halves are mirror images of each other. The distribution on the left is negatively skewed, with its peak shifted toward the upper end of its range and a relatively long negative tail, negative skewed. So the peak is to the right. In a symmetrical scale, it's right in the middle. And in a positively skewed scale, the peak is on the left. The distribution on the right is positively skewed with its peak toward the lower end of its range and a relatively long positive tail. Negatively skewed to the right. Symmetrically skewed in the middle, skewed to the middle, and positively skewed, its peak is on the left. An outlier is an extreme score that is much higher or lower than the rest of the scores in the distribution. Sometimes outliers represent truly extreme scores on the variable of interest. For example, on the Beck's depression inventory, a single clinically depressed person might be an outlier in a sample of otherwise happy and high-functioning peers. However, outliers can also represent errors or misunderstandings on the part of the researcher or participant, equipment malfunctions, or similar problems. And of course, this is an outlier, and this is an outlier. The central tendency of a distribution is its middle, the point around which the scores in the distribution tend to cluster. Another term for central tendency is average. We will consider the three most common measures of central tendency: the mean, the median, and the mode. And this is what it looks like. This is called a bell curve, where the peak is in the middle, right in the middle. The mean of a distribution, symbolized M, is the sum of scores divided by the number of scores. It is an average. As a formula, it looks like this. In this formula, the symbol sigma, the Greek letter sigma, is a summation sign and means to sum across the values of the variable x. N represents the number of scores. The N will always represent the number of scores. The mean is by far the most common measure of central tendency, and there are some good reasons for this. It usually provides a good indication of the central tendency of a distribution, and it is easily understood by most people. The mean has statistical properties that make it especially useful in doing inferential statistics. So the mean actually just means average. So if we add all these numbers up, we get 40. We add all these numbers up, we get 40. And if we divide it by 8, we get 5. And that is the mean. 5 is the mean in this case. An alternative to the mean is the median. The median is the middle score in the sense that half the scores in the distribution are less than it and half are greater than it. The simplest way to find the median is to organize the scores from lowest to highest and locate the score in the middle. When there is an even number of scores, there are 2 scores in the middle of the distribution, in which case the median is the value halfway between. So in this case, we have 1, 3, 3, 6, 7, 8, 9. The median, since there are 7 numbers, is the 4th number, and that would be 6. That is the median. However, if we added all those numbers together, 17, 7, 24, 30, that's 37. That's not right. Is it? Yeah, 37. 37 divided by 7 would be, wait a minute, my brain's not working. 49, 6, 35. It would be 5 something. Yeah, 5.5 and 2/7 would be the median. Would be the mean, I'm sorry, 5 and 2/7. But the median is 6, of course. This is the median number right here. And in this case, we have, since we have an even number, there are 8 numbers, it's somewhere between 4 and 5, not somewhere between 4 and 5. It would be 4.5, would be the median. So let's see what the mean is for that one. That's 17, 23, 28. I'm going backwards. 28, 32, 35, 37, 38. 38 divided by 8. 38 divided by 8 would be 4 and 6/8, or 4 and 3/5, 3/4, 4 and 3/4. So it's almost the same number. The mean would be 4 and 3/4, and the median would be 4.5 or 4.7. Okay. Whoops. Oh. One final measure of central tendency is the mode. The mode is the most frequent score in a distribution. The mode is the only measure of central tendency that can also be used for categorical variables. The mode is the most frequent number, and in this case we have 1, 2, 3 12s and no more 3 12s. So the mode would be 12. In this one we have 3 4s and 3 8s. And which would make the mode both 4 and 8. In a distribution that is both unimodal and symmetrical, the mean, median, and mode will be very close to each other at the peak of distribution. And as we saw, the mean and the mode mean and the median were very close in the ones that we were looking at. In a bimodal or asymmetrical distribution, the mean, median, and mode can be quite different. In a bimodal distribution, the mean and the median will tend to be between the peaks, while the mode will be at the tallest peak. In a skewed distribution, the mean will differ from the median in the direction of the skew, the direction of the longer tail. For highly skewed distributions, the mean can be pulled so far in the direction of the skew that it is no longer a good measure of the central tendency of that distribution. This is why researchers often prefer the median for highly skewed distributions, such as distributions of reaction times. The variability of a distribution is the extent to which the scores vary around their central tendency. Looking at the 2 histograms on the right, both of which have the same central tendency, the mean, median, and mode of each distribution are 10. Notice, however, that the 2 distributions differ in terms of their variability. The top one has relatively low variability, with all the scores relatively close to the center. The bottom one has relatively high variability, with the scores are spread across a much greater range. One simple measure of variability is the range. which is simply the difference between the highest and lowest scores in the distribution. The range of the self-esteem scores in the table on the right is the difference between the highest score, 24, and the lowest score, 15. And of course, that would make the range 9, because between 24 and 15, there are there are 9 places. Although the range is easy to compute and understand, it can be misleading when there are outliers. By far the most common measure of variability is the standard deviation. The standard deviation of a distribution is the average distance between the scores and the mean. Computing the standard deviation involves mathematics. It involves finding the difference between each score and the mean, squaring each difference, finding the mean of these square differences, and finally finding the square root of that mean. And we're going to go through that right now. Okay, so here's our number. These are our numbers. If we add all of these up, 2, 3, 4, there are 8 of them. And so if we add this up, we get 40. And that would make the mean 5. This is x minus the mean. Since it's 5 and we're subtracting 5 from 3, we get a minus 2. 5 from 5 is 0, of course. 5 from 4 is minus 4. 5 from 2 is minus 3, and on and on. And so if we square all of those, we'll get positive numbers. So minus 2 times minus 2 would be 4. 0, of course, would be 0. Minus 1 times 1 is 1. Minus 1 times minus 1 is 1. Minus 3 times minus 3, of course, is 9. And on and on, on and on. So what we get is, when we add all of those up, we get 28. Divide that by 28 by 8, we get 3.50, and the square root of 3.50 is 1.87. So that's the standard deviation. So the average difference between the mean and the results is 1.87. So if we were going to report this out, if we were doing a poll, oh, did you guys hear that Biden dropped out of the presidential race? He's endorsing his vice president, Kamala Harris. That should be interesting to watch this play out. Be interesting to see who she picks as her vice president. So if we were doing a poll and we had these numbers and we were saying, well, how accurate are they? We would do a standard deviation. The standard deviation in this case, well, the mean is 5. So what does that mean? Well, that means the mean is 5, but it's plus or minus 1.87. That would be the standard deviation. So it could be anywhere. So a 5 could be anywhere between 6.87 and 3.23. Is that right? Or something like that. If you've already taken a statistics course, which you were supposed to before you took this class, I let people in because I didn't think the only statistics in this class really are the last 2 chapters, the descriptive statistics and the inferential statistics. So I figured, yeah, most people can figure this out. Maybe I can explain it so it makes sense. If you've already taken a statistics course, you may have learned to divide the sum of squared differences by n minus 1 rather than by n when you compute the variance and standard deviation. Now this is interesting because when I read this, I kept getting 2 different formulas, n and n minus 1. So I called my son and I asked him, what in the world's going on here? And he had to look it up, and he He gave me this information, and then it was actually in the book. So this is the information my son gave me. By definition, the standard deviation is the square root of the mean of the squared differences. That would be that one. This implies dividing the sum of squared differences by n, as in the formula just presented, like this. Computing the standard deviation this way is appropriate when your goal is simply to describe the variability in a sample. And learning it this way emphasizes that the variance is in fact the mean of the squared differences, and the standard deviation is the square root of the mean. Now, when we talk about the difference between the population and the sample, if our population is 1,000 people and our sample is 100 people, then potentially the level of error would be greater for the sample because there are fewer people, we might be picking people right from the middle. So in order to make this standard deviation accurate, you have to do n minus 1. If we have the entire population that we're looking at, then that error goes away because we're looking at everyone, and therefore we can just divide it by the mean rather than the mean minus 1. This shows that there is more possibility of error, and that's why it is n minus 1. That's the way it was explained to me by my son. So if it doesn't make any sense to you, you can blame him. Most calculators and software packages divide the sum of squared differences by n minus 1. This is because the standard deviation of a sample tends to be a bit lower than the standard deviation of the population the sample was selected from. Dividing the sum of squares by n minus 1 corrects for this tendency and results in a better estimate of the population standard deviation. Because researchers generally think of their data as representing a sample selected from a larger population, and because they are generally interested in drawing conclusions about the population, it makes sense to routinely apply this correction. And for that reason, and that's the same explanation my son gave me. The percentile rank of a score is the percentage of the scores in the distribution that are lower than that score. For any score in the distribution, we can find its percentile rank by counting the number of scores in the distribution that are lower than that score and converting that number to a percentage of the total number of scores. Percentile ranks are often used to report the results of standardized tests of ability or achievement. If your percentile rank on a test of verbal ability were 40, for example, this would mean that you scored higher than 40% of the people who took the test. And if you've ever had an SAT test, that's the way it was reported out. You're in the 95th percentile, or you're in the 50th percentile, or you're in the 75th percentile. Another approach to distribution is the z-score. The z-score for a particular individual is the difference between the individual's score and the mean of the distribution divided by the standard deviation of the distribution. And this is the formula. A z-score indicates how far above or below the mean a raw score is, but it expresses this in terms of the standard deviation. For example, in a distribution of intelligence quotient scores with a mean of 100 and a standard deviation of 15, an IQ score of 110 would have a z-score of 0.67. In other words, a score of 110 is 0.67 standard deviations, approximately 2/3 of a standard deviation above the mean. Similarly, a raw score of 85 would have a z-score of 85 minus 100 over 15, which is 1.0, negative 1.0. In other words, a score of 85 is one standard deviation below the mean. There are several reasons that z-scores are important. They provide a way of describing where an individual's score is located within a distribution and are sometimes used to report the results of a standardized test. They provide one way of defining outliers, Outliers are sometimes defined as scores that have z-scores less than -3 or greater than +3. They are defined as scores that are more than 3 standard deviations from the mean. Z-scores play an important role in understanding and computing other statistics. Z-score is a numerical measurement that describes a value's relationship to the mean of the group of values and is measured in terms of standard deviations from the mean. As we have seen throughout this book, most interesting research questions in psychology are about statistical relationships between variables. Differences between groups or conditions are usually described in terms of the mean and the standard deviation of each group or condition. Thomas Olendick and his colleagues conducted a study in which they evaluated two one-session treatments for simple phobias in children. And this was done in 2009, and this is a picture of Dr. Olendick. They randomly assigned children with an intense fear, for example, to dogs, to one of three conditions. Either they used exposure conditioning, the children actually confronted the object of their fear under the guidance of a trained therapist. They used education conditioning, they learned about the phobias and some strategies for coping with them, or they were put on a wait list, which became their control. They were waiting to receive a treatment after the study was over. The severity of each child's phobia was then rated on a 1 to 8 scale by a clinician who did not know which treatment the child had received. This was one of several dependent variables. The mean fear rating in the education condition was 4.83 with a standard deviation of 1.52, while the mean fear rating in the exposure condition was 3.47 with a standard deviation of 1.77. The mean fear rating in the control condition was 5.56 with a standard deviation of 1.21. In other words, both treatments worked, but the exposure treatment worked better than the education treatment. And this is a histogram showing that very thing, showing what I just said. So the people with the highest phobias were the individuals that hadn't received any treatment. The ones who were educated came in at 4.83, and the ones who were exposed to their phobias, their level of phobia, their level of fear was 3.47. It is important to be able to describe the length. It is important to be able to describe the strength of a statistical relationship, which is often referred to as the effect size. The most widely used measure of effect size for differences between group or condition means is called the Cohen's d, which is the difference between the two means divided by the standard deviation. Now this is really kind of interesting because the last time I taught this class, Cohen's d was not being accepted as standard, and now it is. So this is something that has changed since the last time I taught this class. As curious as that is. We didn't talk about Cohen's d. I looked in my old textbook. It's not even in there at all. As a matter of fact, they didn't even talk about effect sizes. So this is really kind of interesting. Thomas Cohen is the one that came up with this, with the idea of the Cohen's d. And it's quite interesting the way it works, and it does make a lot of sense. In this formula, it does not really matter which mean is M1 and which is M2. If there is a treatment group and a control group, the treatment group mean is usually M1 and the control group mean is M2. And what we're looking for is the effect size. What we're looking for is the difference between the two variables. So we subtract that and then divide by the standard deviation. Otherwise, the larger mean is usually M1 and the smaller mean M2, so that Cohen's d turns out to be positive. Indeed, Cohen's d values, and it should be. I mean, if we're talking about a variable, then it should be a positive number. Indeed, Cohen's d values should always be positive, so it is the absolute difference between the mean that is considered in the numerator. I mean, if we're talking about phobias and you treated somebody and their phobia became worse, that means that your treatment not only didn't work, but it made things worse. That's not good. The standard deviation in this formula is usually a kind of average of the two group standard deviations called the pooled within group standard deviation. To compute the pooled within group standard deviation, add the sum of the squared differences for group 1 to the sum of squared differences for group 2. Divide this by the sum of the two sample sizes and then take the square root of that. Informally, however, the standard deviation of either group can be used instead. Cohen's d is the difference between the two means expressed in standard deviation units. Notice its similarity to a z-score, which expresses the difference between an individual score and a mean in standard deviation units. A Cohen's d of 0.50 means that the two group means differ by 0.50 standard deviations, or half a standard deviation. A Cohen's d of 1.20 means that they differ by 1.20 standard deviations. Values near 0.20 are considered small, values near 0.50 are considered medium, and values near 0.80 are considered large. Thus, a Cohen's d value of 0.50 represents a medium-sized difference between two means, and the Cohen's d value of 1.20 represents a very large difference in the context of psychological research. In the research by Olendick and his colleagues, there was a large difference. The difference was 0.82 between the exposure and the education conditions, and so that puts it right here, strong or large. The term effect size can be misleading because it suggests a causal relationship, that the difference between the two means is an effect of being in one group or condition as opposed to another. But as we have learned throughout the text, causal empirical research is rare. Many interesting statistical relationships take the form of correlations between quantitative variables. Carlson and Conrad in 2011 conducted a study on the relationship between the alphabetical position of the first letter of a people's last name, from A equals 1 and Z equals 26, and how quickly these people responded to consumer appeals. In one study, they sent emails to a large group of MBA students offering free basketball tickets from a limited supply. The result was that the further toward the end of the alphabet students' last names were, the faster that they tended to respond. Okay, and I was thinking about this. I was thinking about this research, and I was thinking, why in the world would that be? Shouldn't everybody respond exactly the same? And the answer that I came up with was that if you've got a group of people that you're going to offer tickets to, like what Carlson and Conrad did, and you decided to do it by alphabetical order, the first people you talk to would be the A, B, C, D, E, F. Those would be your first group, and they might still be thinking about it. But by the time you get to the W, X, Y, Z, those people, they've already had all these other people being offered the tickets, and they've had a lot of time to think about it. So they know if they want it or if they don't. So this makes a lot of sense because we do a lot of things in alphabetical order. Classrooms are always arranged in alphabetical order. They tend to be, especially in primary and secondary school. Such relationships are often presented using line graphs or scatter plots, which show how the level of one variable differs from the range of the other. The scatter plot shows the relationship between 25 research methods students' scores on the Rosenberg self-esteem scale given on 2 occasions a week apart. Here the points represent individuals, and we can see that the higher students scores on the first occasion, the higher they tended to score on the second occasion. In general, the line graphs are used when the variable on the x-axis has or is organized into a small number of distinct values, such as the four quartiles of the named distribution. Scatter plots are used when the variable on the x-axis has a large number of values, such as the different possible self-esteem scores. And of course, they did everything twice. So rather than a circle, this looks like an egg. Why does it look like an egg? Because it's got one circle on top of the other. And one was higher than the other. And the same way with all of these. Both of the previous examples are linear relationships in which the points are reasonably well fit by a single straight line. Nonlinear relationships are those in which the points are better fit by a curved line. The graph on the right shows a hypothetical relationship between the amount of sleep people get per night and their level of depression. In this example, the line that best fits the points is a curve, a kind of upside down U. Because people, it's not upside down, because people who get about 8 hours of sleep tend to be the least depressed, while those who get too little sleep and those who get too much sleep tend to be more depressed. Linear relationships are not uncommon in psychology. The strength of a correlation between quantitative variables is typically measured using a statistic called Pearson's R. Its possible values range from -1 through 0 to +1. A value of 0 means there is no relationship between the two variables. In addition to this guidelines for interpreting Cohen's D, Cohen offered guidelines for interpreting Pearson's R in psychological research. Values near 1 plus or minus 1 are considered small. Values near plus or minus 3 are considered medium. And values near plus or minus 0.50 are considered large. Pearson's R values of plus 0.30 and minus 0.30 are equally strong. It is just that one represents a moderate positive relationship and the other a moderate negative relationship. Like Cohen's D, Pearson's R is also referred to as a measure of effect size, even though the relationship may not be a causal one. APA style includes several rules for presenting numerical results in the text. These include using words only for numbers less than 10 that do not represent precise statistical results and using numerals for numbers 10 and higher. Statistical results are always presented in the form of numerals rather than words and are usually rounded to 2 decimal places. For example, 2.00 rather than 2 or 2. They can be presented either in the narrative description of the results or parenthetically, much like reference citations. When you have a small number of results to report, it is often most efficient to write them out. Here are some examples. The mean age of the participants was 22.43 years, with a standard deviation of 2.34. In general, scatter plots, bar graphs, and line graphs should be slightly wider than they are tall. The independent variables should be plotted on the x-axis and the dependent variable on the y-axis. Values should increase from left to right on the x-axis and from bottom to top on the y-axis. The x-axis and y-axis should begin with the value 0. 0 right there. Okay. Axis labels should be clear and concise and include the units of measurement if they do not appear in the caption. Axis labels should be parallel to the axis. Legends should appear within the figure. Text should be in the same simple font throughout and no smaller than 8 point and no larger than 14 point. Captions are titled with the word figure, followed by the figure number in the order in which it appears in the text, and terminated with a period. This title is italicized, just like you see right here. After the title is a brief description of the figure terminated with a period, for example, reaction times of the control versus experimental groups. Following the description include any information needed to interpret the figure, such as any abbreviations, units of measurement, if not on the axis label, and units of error bars. And this is a joke. I think we should give it another shot. We should break up and I can prove it. And she shows him this chart. Huh? Maybe you're right. I knew data would convince you. No, I just think I can do better than someone who doesn't label her axes. And she didn't. So that has no meaning. Bar graphs are generally used to present and compare the mean scores for two or more groups or conditions. Smaller vertical bars that extend both upward and downward from the top of each bar are error bars, and they represent the variability in each group or condition, and these are the error bars. The standard error is the standard deviation of the group divided by the square root of the sample size of the group. The standard error is used because, in general, a difference between group means that is greater than two standard errors is statistically significant. Thus, one can see whether a difference is statistically significant based on a bar graph with error bars. Line graphs are used when the independent variable is measured in a more continuous manner, for example, time, or to present correlations between the quantitative variables when the independent variable has or is organized into a relatively small number of distinct levels. Each point in a line graph represents the mean score on the dependent variable for participants at one level of the independent variable. Scatter plots are used to present correlations and relationships between quantitative variables when the variable on the x-axis, typically the independent variable, has a large number of levels. Each point in a scatter plot represents an individual rather than the mean for a group of individuals, and there are no lines connecting the points. When the variables on the x-axis and y-axis are conceptually similar and measured on the same scale, this can be emphasized by making the axes the same length. When two or more individuals fall at exactly the same point on the graph, one way this can be indicated is by offsetting the point slightly along the axis. Other ways are by displaying the number of the individuals in parentheses next to the point, or by making the point larger or darker in proportion to the number of individuals. Finally, the straight line that best fits the points in that scatter plot, which is called the regression line, can also be included. I almost fell asleep trying to read the word regression. Here, let me take a drink. And that shows you the different scatter plots. This is a positive correlation. This is a negative correlation. And this is no correlation whatsoever. Now, that's kind of interesting. Whoever put this together separated scatter and plots, but it's probably European. But in the United States, of course, we put the two words together. Like graphs, tables can be used to present large amounts of information clearly and efficiently. Then the same general principles apply to tables as apply to graphs. They should add important information to the presentation of your results, be as simple as possible, and be interpretable on their own. The most common use of tables is to present several means and standard deviations, usually for complex research designs with multiple independent and dependent variables. The table includes horizontal lines spanning the entire table at the top and bottom, and just beneath the column headings. Every column has a heading, including the leftmost column, and there are additional headings that span two or more columns that help to organize the information and present it more efficiently. Another use of the table is to present correlations, usually measured by Pearson's R among several variables. This kind of table is called a correlation matrix. Only half the table is filled in because the other half would have identical values. The correlation of a variable with itself is always 1.00. So these values are replaced by dashes to make the table easier to read. In this case, they didn't put the dashes in, but we know that those numbers don't mean anything. The numbers that are missing are not important. Even when you understand the statistics involved, analyzing data can be a complicated process. There are a few things you should do before you begin analyzing your data. Be sure that they do not include any information that might identify individual participants, and be sure that you have a secure location where you can store the data and a separate secure location where you can store any consent forms. Unless the data are highly sensitive, a locked room or password-protected computer is usually good enough. It is also a good idea to make photocopies or backup files of your data and store them in yet another secure location, at least until the project is completed. Professional researchers usually keep a copy of their raw data and consent forms for several years in case questions about the procedure, the data, or participant consent arise from the project when the project is completed. And of course, I still have all my raw data from my dissertation. That was 12 years ago. Check your raw data to make sure that they're complete and appear to have been accurately recorded, whether it was participants, yourself, or a computer program that did the recording. At this point, you might find that there are illegible or missing responses or obvious misunderstandings. You will have to decide whether such problems are severe enough to make a participant's data unusable. In the information about the main independent or dependent variable is missing, or if several responses are missing, are suspicious, you may have to exclude the participant's data from the analysis. If you do decide to exclude any data, do not throw them away or delete them because you or another researcher might want to see them later. Instead, set them aside and keep notes about why you decided to exclude them, because you will need to report this information. You're ready to enter your data in a spreadsheet program, or if it is already in a computer file, to format it for analysis. You can use a general spreadsheet program like Microsoft Excel or a statistical analysis program like SPSS to create your data file. Data files created in one program can usually be converted to work with other programs. The most common format is for each row to represent a participant and for each column to represent a variable, with the variable name at the top of each column. Although category labels are often clearer, some analyses might require numbers. SPSS allows you to enter numbers, but also attach a category label to each number. Before turning to your primary research questions, there are often several preliminary analyses to conduct. For multiple response measures, you should assess the internal consistency of the measure. Statistically, programs like SPSS will allow you to compute Cronbach's alpha or Cohen's K. If this is beyond your comfort level, you can still compute and evaluate a split half correlation. You should analyze each important variable separately. This step is not necessary for manipulated independent variables, of course, because you as the researcher determine what the distribution would be. Make histograms for each one, note their shapes, and compute the common measures of central tendency and variability. Be sure that you understand what these statistics mean in terms of the variables you are interested in. Now is the time to identify outliers, examine them more closely, and decide what to do with them. You might discover that what at first appears to be an outlier is the result of a response being entered incorrectly in the data file, in which case you only need to correct the data file and move on. Alternatively, you might suspect that an outlier represents some other kind of error, misunderstanding, or lack of effort by a participant. It can be justifiable to exclude the outlying response or participant from the analyses. If you do this, you should keep notes on which responses or participants you have excluded and why, and apply those same criteria consistently to every response and every participant. When you present your results, you should indicate how many responses or participants you excluded and the specific criteria that you used. Do not literally throw away or delete the data that you choose to exclude. Set them aside because you or another researcher might want to see them later. Outliers do not necessarily represent an error, misunderstanding, or lack of effort. They might represent truly extreme responses or participants. Although scores might represent errors, misunderstandings, or even intentional exaggerations, it is also plausible that they represent honest and even accurate estimates. One strategy would be to use the median and other statistics that are not strongly affected by the outliers. Another would be to analyze the data, both including and excluding any outliers. If the results are essentially the same, which they often are, then it makes sense to leave the outliers. If the results differ depending on whether the outliers are included or excluded, then both analyses can be reported, and the differences between them discussed. You are ready to answer your primary research questions. When you designed your study, you might have had a hypothesis that a particular relationship might exist in the data. In this case, you would conduct a planned analysis to test a relationship that you're expected in the hypothesis. And when you do these things, when you do a dissertation or a thesis for your master's degree, you have to tell them what kind of statistics you're going to be using. Well, coming up with statistics that you're going to be using with your hypothesis is known as planned analysis. If you expected a difference between group or condition means, you can compute the relevant group or condition means and standard deviations, make a bar graph to display the results, and compute Cohen's d. If you expected a correlation between quantitative variables, you can make a line graph or a scatter plot and compute Pearson's R. Once you have conducted your planned analysis, you can move on to examine the possibility there might be a relationship in the data that you did not hypothesize. This would be an exploratory analysis, an analysis that you are undertaking without an existing hypothesis. These analyses will help you explore your data for other interesting results that might provide the basis for future research and material for the discussion section of your paper. Daryl Bim in 2003 suggested that you examine your data before from every angle. It is important to differentiate planned from exploratory analyses in writing your results in discussion sections of your report. This is because complex sets of data are likely to include patterns that occurred entirely by chance, and every time you do another unplanned analysis on these data, you increase the likelihood these chance patterns will appear to be real patterns. That is referred to as a type 1 error. Thus, results discovered while doing exploratory analyses what Bim calls a fishing expedition, should be viewed skeptically and replicated in at least one new study before being presented. If you do find interesting relationships you did not expect in the data, explain that they might be worthy of additional research. And that is it. And I apologize for falling asleep a couple times while I was doing this. One thing that happens to me, I'm old, okay? And sometimes when I'm talking so much, carbon monoxide builds up. And I have to take a deep breath. And sometimes when I take a deep breath and I didn't get very much sleep last night, it makes me have to wake myself up. I apologize. I'm not drunk, I promise. Anyway, next week is the last week. We'll talk about inferential statistics. And there you go. Okay. So next week.